The heart of a galaxy holds its entire life story. This journey of galactic cores is one of the universe's most epic slow-motion transformations, a narrative written over billions of years. By the end of this exploration, you will understand the fundamental forces that dictate the birth, life, and death of galaxies. What mysterious engine awakens at a galaxy's center to reshape its entire destiny? And how does our own Milky Way's quiet core hide a dramatic past? What does the fate of a galaxy truly depend upon? That dense, swirling heart of a galaxy begins not as a brilliant beacon, but as a quiet, cosmic seed. Picture the universe in its youth, vast clouds of primordial gas and mysterious dark matter drifting in the darkness. Gravity is the great sculptor here, patiently pulling these clouds inward, causing them to slowly collapse and rotate. At the very center of this immense, swirling whirlpool, the gas becomes incredibly thick and hot. This is the birth of the galactic core, a gravitational anchor point that will dictate the entire future of the galaxy taking shape around it. Within this dense, chaotic nursery, the first generations of stars ignite. These are not the stable, long-lived stars we know today, but colossal, short-lived giants. They burn furiously and die young in spectacular supernova explosions, seeding the surrounding gas with the first heavy elements. The core region is a frenetic place, a constant cycle of violent star birth and star death. Furthermore, these infant galaxies are not isolated. They frequently collide and merge with their neighbors, a chaotic dance that funnels even more gas and energy into their burgeoning hearts. What is truly fascinating, however, is what is missing from this scene. The supermassive black holes that dominate the centers of modern galaxies like our own were not present at this early stage. The primordial core was a place ruled by the raw power of gravity and star formation, not by the terrifying appetite of a black hole. This fundamental difference marks the starting line for an epic journey, a transformation so profound it will rewrite the very nature of the galaxy itself. But a new power was slowly awakening in the heart of that stellar nursery. The chaotic dance of merging galaxies and collapsing gas clouds created the perfect conditions for a gravitational monster to be born. This is the first great transformation, the emergence of the central supermassive black hole. It does not appear fully formed. Instead, it grows gradually, a patient accumulation of mass over cosmic time. A massive gas cloud might collapse directly under its own immense weight, bypassing star formation entirely to birth a black hole seed. Alternatively, smaller black holes, the remnants of those first giant stars, could spiral inward and merge, their masses combining into something far greater. Once present, this gravitational behemoth begins to dictate the core's entire rhythm. Stars and gas now move to its tune, their orbits shaped by its immense, invisible pull. Yet its most profound influence comes not from its gravity alone, but from its appetite. As the black hole feeds, pulling in vast amounts of gas and dust, the material does not simply vanish. It swirls into a superheated disk, a cosmic whirlpool of incandescent plasma. In this process, known as accretion, friction and magnetic fields heat the material to millions of degrees, releasing a staggering flood of energy. This outpouring of radiation and powerful jets of particles acts like a cosmic wind, blowing outward through the core. This is the pivotal moment. That very energy which signifies the black hole's growth begins to forcefully reshape its home. It heats the surrounding gas, preventing it from cooling and collapsing to form new stars. The core's frenetic era of rampant star birth is systematically shut down. The region transitions from a place ruled by the collective light of billions of stars to one governed by the concentrated, terrifying power of a single entity. This shift marks a fundamental turning point, a new chapter where the black hole's own life cycle begins to write the destiny of the entire galaxy. This quiet reign of a lone black hole, however, is often shattered by cosmic violence. Galactic mergers are not just dramatic events, they are powerful agents of core transformation. When two galaxies collide, it is a slow, gravitational dance spanning hundreds of millions of years. Their central black holes, each the ruler of its own domain, are dragged toward the new common center of gravity. They begin a tight orbital embrace, forming a binary system that churns the very fabric of space and time around them. This cosmic dance is the primary engine for feeding the central monster. The merger funnels absolutely colossal amounts of gas and dust directly into the core, like rivers of fuel suddenly flooding a dormant engine. This triggers an explosive burst of new star formation, a final, brilliant starburst. But more importantly, it provides a feast for the central black hole. As it gorges on this incoming material, the accretion disk blazes with unimaginable intensity, and the core lights up as a quasar, outshining the entire galaxy. This is the core's most active and luminous phase. The gravitational turmoil of the merger also violently stirs the stellar population, stripping countless stars from their orderly orbits and flinging them into new paths. This reshuffles the core's mass, altering its density and structure forever. These violent episodes are cosmic renovations, fundamentally remodeling the galactic center in a way that peaceful, isolated evolution simply cannot match. They accelerate the core's life story, pushing it rapidly toward its next, and often final, evolutionary stage. Yet the most common transformation of a galaxy's heart is not born from collisions, but from a quiet, internal rhythm. This is the process of secular evolution, a slow and persistent reshaping driven by the galaxy's own structure. Over billions of years, subtle instabilities emerge within the galactic disk. A central bar of stars might form, or the majestic spiral arms themselves can act like cosmic conveyor belts. These structures do not channel material with the violent force of a merger, but with a gentle, relentless pull. They redirect gas from the outer regions on a slow, drifting journey inward toward the core. This is not a sudden flood of fuel, but a steady trickle. This gradual inflow sustains a low level of activity in the waiting supermassive black hole, allowing it to glow with a soft, persistent light rather than the blinding flash of a quasar. More subtly, this same incoming gas provides the raw material for new stars to form right in the galactic center. Over eons, these stars can accumulate into a dazzling, dense nuclear star cluster, a glittering jewel set in the heart of the galaxy. This slow and steady process refines the core, making it more compact and ordered without any external drama. It is the cosmic equivalent of erosion patiently carving a canyon, a testament to the immense power of patience in the universe. There was a cosmic epoch when the hearts of galaxies blazed with unmatched ferocity. This was the Quasar Era, a period peaking some 10 billion years ago, when the core of nearly every large galaxy was a beacon of terrifying brilliance. The engine behind this light was the supermassive black hole in its most active state, gorging on gas at a phenomenal rate. As matter spiraled into the abyss, its final moments were spent in a blazing disk of incandescent plasma, releasing so much energy that a single quasar could outshine a trillion stars. For a time, the core was not defined by the gentle light of its stellar citizens, but by the raw, concentrated power of its central monster. This immense energy output was not just a spectacle, it was a transformative force. The radiation and powerful particle jets streaming from the active nucleus acted as a cosmic hurricane, slamming into the surrounding clouds of gas. This is the critical feedback mechanism that fundamentally reshaped the galaxy's destiny. The very gas that was the raw material for new stars was violently heated and blown clear out of the core. Star formation, the core's primary activity for billions of years, was systematically and forcefully shut down in a process astronomers call quenching. It is a powerful act of self-regulation, where the black hole's own growth spurt prevents the galaxy from becoming even larger. This brilliant but destructive phase was a necessary cosmic pruning. By clearing out the natal gas, the quasar ensured that the core's stellar population would age without significant renewal. The chaotic, youthful stellar nursery was forever calmed, its potential for future growth severely limited. The brilliant flash of the Quasar Era, while relatively brief, left a permanent mark. It carved out the core's inner structure, dictated the final census of its stars, and set the stage for the long, quiet twilight that would follow. Nestled deep within the galactic heart, often in the very same space ruled by a supermassive black hole, lies another marvel of cosmic architecture, the nuclear star cluster. Picture the core of our own Milky Way, not just as the home of a dark giant, but as a dazzling stellar metropolis, one of the densest and most dynamic places in the entire galaxy. These clusters are not random assortments of stars. They are ancient cities built through two distinct and powerful construction methods. The first is local construction, where gas gently funneled inward by the galaxy's secular evolution cools and collapses, forming new stars right in the central square. The second method is more like urban renewal through cosmic acquisition. Entire globular clusters, which are dense spherical cities of stars orbiting the galaxy, can be dragged by gravitational forces over billions of years. They slowly spiral inward, their orbits decaying until they are finally merged and absorbed into the growing central cluster. This process adds ancient stellar populations to the mix, creating a complex demographic tapestry. This dual origin story makes the nuclear cluster a unique historical archive. By studying the ages and motions of its countless stars, astronomers can read the core's biography. They can identify the quiet periods of steady growth and pinpoint the violent merger events that delivered old globular clusters to the center. The presence of this glittering, dense stellar city adds a profound layer of complexity to the galactic core, transforming it from a simple engine room into a vibrant capital city, whose very structure tells the story of its long and eventful life. The galactic core is a gravitational racetrack where stars move at speeds that defy comprehension. Their paths are not serene orbits, but chaotic trajectories sculpted by two immense forces: the relentless pull of the central supermassive black hole and the combined gravity of the densely packed stellar city surrounding it. This environment is so extreme that a star can complete a full orbit in just a few Earth years, whipping around the center at millions of kilometers per hour. This is not a placid, orderly dance. It is a frenetic scramble where every star is constantly influenced by the gravitational pull of its countless neighbors. This slow, persistent process, known as relaxation, gradually reshuffles stellar orbits over millions of years. Think of it like a cosmic billiards game on an unimaginable scale. Each gentle gravitational nudge from a passing star alters another's path just a little, a slow-motion chaos that accumulates over eons. The consequences of this stellar pinball are profound. Some stars, through a series of fortunate gravitational kicks, gain tremendous speed and are flung clear out of the galaxy entirely, becoming lonely hypervelocity stars racing into the intergalactic void. Others suffer the opposite fate, their orbits decaying until they venture too close to the central black hole and are torn apart by its immense tidal forces, their material adding to the black hole's growth in a brilliant flare of light. This constant churning acts like a gravitational mixer, slowly changing the core's density and structure over cosmic time. The most massive stars tend to sink toward the very center through these interactions, while lighter stars are more easily scattered outward. This stellar dynamics is the invisible engine that constantly remodels the galactic heart, ensuring that its appearance and the very distribution of its mass are never truly static, but always evolving in a slow, relentless gravitational ballet. This balancing act between creation and destruction is written into the very fabric of galactic cores. The energy blasting from an active supermassive black hole does far more than just create a brilliant light show. It actively engineers its own environment. This process, known as AGN feedback, is a dominant force in the core's long-term evolution. Think of it as a cosmic thermostat. When the black hole feeds too greedily, the resulting outpouring of radiation and powerful, focused jets of particles acts like a colossal heating system. It slams into the vast clouds of cool gas, the very raw material for new stars, and violently heats it. This prevents the gas from ever cooling down and collapsing under its own gravity. The core's stellar nursery is effectively switched off. This is how a galaxy's heart can be quenched. Its vibrant blue star forming regions fading over billions of years into the calm, red glow of aging stars. We see the end result of this process in the so-called red and dead elliptical galaxies, massive systems where star formation has been completely and permanently shut down. Their cores are quiet, their stories largely complete. The brilliance of this feedback mechanism is its self-regulating nature. If the black hole becomes too active, it blows away its own fuel supply and goes quiet. Without that energetic output, gas can once again accumulate and cool, potentially restarting the cycle. It is a delicate cosmic dance, where the tiny central engine governs the fate of the entire galaxy, linking the physics of an accretion disk smaller than our solar system to the large-scale properties of a structure hundreds of thousands of light-years across. This single process explains so much of the diversity we see in galaxy cores today, from the violently star-bursting to the profoundly silent, each a testament to the different chapters in this ongoing story of feedback and transformation. The vibrant color of a galaxy's core is a direct reflection of its life story. A brilliant blue heart signals a stellar nursery in its prime, filled with young, massive stars that burn hot and fast, shining with an intense blue-white light. These stars are the universe's prodigies, living spectacular but short lives. Their dominance paints the entire core in cool, energetic tones. Yet this blue phase cannot last. As the core evolves, the very processes we have explored begin to exert their influence. The immense feedback from an active black hole heats and expels the gas. Mergers subside and stop funneling in new fuel. And the slow, steady inflow of secular evolution may also dwindle. The reservoir of cold gas, the raw material for new stars, is depleted. Without this fuel, the formation of new blue giants grinds to a halt. The existing massive stars, having lived their short lives, soon meet their end in dramatic supernova. What remains is the quieter, longer-lived population of smaller stars. These stellar retirees are cooler and redder, burning their fuel with a slow, steady patience that spans billions of years. With the blue giants gone, their collective reddish glow comes to dominate the core's appearance. This transition from blue to red is one of the most fundamental shifts in a galaxy's long life. It is the visual signature of a core moving from a youthful, active state to a mature, quiescent one. By observing galaxies at different distances, and therefore looking back in time, astronomers can watch this color change unfold. They can map out how the quenching of star formation swept through the universe, turning the brilliant blue hearts of youthful galaxies into the calm, red embers of the ancient cosmic giants we often see today. Yet beneath the visible light of stars and the brilliant glow of quasars lies a deeper, more elusive mystery tied to the very fabric of the cosmos. The transformation of a galactic core is not just a story of stars and black holes. It is also a narrative written in the invisible ink of dark matter. For decades, our most successful cosmological model, known as cold dark matter, has used powerful computer simulations to trace the growth of galaxies. These simulations consistently predict a specific architecture for the dark matter halo that surrounds every galaxy. They show the halo's density should rise steeply, forming a sharp peak or cusp right at the very center, coinciding with the galactic core. This seemed like a solid, fundamental prediction, but the universe, as it often does, had a surprise in store. When astronomers measured the actual mass distribution in the cores of many smaller, dwarf galaxies, they found something profoundly different. Instead of a steeply rising cusp, the dark matter density appeared constant, forming a flat, plateau-like core. This glaring mismatch between theoretical prediction and direct observation is known as the Core-Cusp problem, and it represents one of the most significant puzzles in modern astrophysics. So what could be smoothing out the predicted dark matter peak? The leading hypothesis points directly back to the energetic processes we have been exploring. Imagine the cumulative effect of billions of years of violent activity in the galactic heart. Each outburst from the active supermassive black hole, with its powerful jets and intense radiation, and each wave of supernova explosions from dying stars, acts like a cosmic piston. These events pump immense energy into the central region, not just stirring the gas and stars, but potentially pushing against the very gravitational framework of the dark matter halo itself. This constant, energetic churning could be enough to physically redistribute the dark matter, gravitationally scattering it outward and eroding the sharp central cusp into a gentler, flatter core. It is a remarkable idea that the tiny, brilliant engine of a black hole could be sculpting the largest, most invisible structure in the galaxy. Solving the Core-Cusp problem is therefore a two-fold quest. It forces us to refine our understanding of how galactic cores evolve, acknowledging that their most dramatic transformations might involve reshaping the dark matter itself. But it also serves as a crucial test for the fundamental nature of dark matter. Does its behavior in these extreme environments match our theories, or does its apparent smoothing hint at properties we have not yet dreamed of? The answer is written in the silent, dark heart of every galaxy, waiting to be read. Sometimes a star's orbit brings it fatally close to the central black hole. When the gravitational pull on the side of the star nearest the monster vastly exceeds the pull on its far side, the star is stretched, a process known as spaghettification, and then torn completely apart. This is a tidal disruption event, a sudden and brilliant flare that can briefly outshine every star in the galaxy combined. But this cosmic violence serves a deeper purpose in the core's long-term evolution. It is a critical mechanism of cleanup and change. The debris from the shattered star does not simply vanish. About half of it forms a swirling, superheated accretion disk around the black hole, fueling a brilliant but short-lived outburst of energy as the material is consumed. The other half of the stellar material is flung away at tremendous speeds, ejected entirely from the core region by the immense forces at play. This ejection is a permanent removal of mass. Over millions and billions of years, each of these events acts like a careful curator, slowly thinning out the stellar population in the black hole's immediate neighborhood. Each star destroyed is one less gravitational influence in that chaotic inner region, subtly lowering the density of the core over cosmic time. Through this process of gradual attrition, tidal disruption events contribute to the long-term sculpting of the galactic heart, one stellar cataclysm at a time. The most telling clue to this cosmic symbiosis is not a brilliant flash of light, but a simple, silent graph. When astronomers plot the mass of a galaxy's central bulge of stars against the mass of its supermassive black hole, a remarkable pattern emerges. The two are locked in a tight correlation, a direct proportionality that spans galaxies of all shapes and sizes. A larger stellar bulge always hosts a more massive black hole. This is not a coincidence. It is the fossil record of a deep, fundamental partnership, a dance of construction and regulation that has been ongoing for billions of years. The same cosmic processes that build the galaxy also feed its dark heart. Major galactic mergers do not just trigger bursts of star formation in the bulge. They also funnel torrents of gas directly to the central black hole, causing it to grow. The slower, gentler process of secular evolution steadily builds the central star cluster, while simultaneously providing a trickle of fuel to sustain the black hole. Growth on one side promotes growth on the other, but this is not a one-way street. The black hole gives back in a powerful and often destructive way. When it feasts and becomes an active quasar, the resulting energy blast heats and expels the surrounding gas. This feedback shuts down star formation not only in the core, but throughout the entire galaxy. The very growth of the black hole ultimately terminates the growth of the stellar population around it. This self-regulating loop ensures that the two masses remain in balance. They grow together, and they quiet down together. This co-evolution means you cannot understand the life of a galaxy without understanding the life of its black hole. The fate of the entire sprawling star system, with its hundreds of billions of stars, is intimately tied to the tiny, dark engine at its very center. Their stories are not separate, but a single intertwined narrative written across cosmic time. The universe today offers us a living museum of galactic hearts, each one a frozen moment in a billion-year story. Our own Milky Way presents a relatively quiet core, where a dormant supermassive black hole slumbers, and new stars are born at a gentle, steady pace. This calm scene is just one possible outcome. In the vast elliptical galaxies, we find cores that are truly red and dead. Their gas supplies long since vanished, their stellar populations ancient and quietly fading. There is no star formation here, only the slow, collective red glow of countless aging suns. Then there are the spectacular engines, like the one at the heart of Galaxy M87, where a supermassive black hole actively feasts, launching jets of plasma at near light speed that stretch for thousands of light years into the intergalactic void. This stunning diversity is not random. It is a direct consequence of a galaxy's birth weight, its violent history of collisions, and the richness of its cosmic neighborhood. A galaxy that experienced frequent, violent mergers in its youth was likely to funnel immense amounts of gas to its center, triggering a brilliant quasar phase that ultimately exhausted its fuel and left behind a red and dead giant. A galaxy born in a more isolated environment, or with a slower, internal rhythm of growth, might have nurtured a quieter core like our own. Each type of core we observe is a fossil, a preserved chapter in the grand narrative of transformation. By simply cataloging this cosmic menagerie, we can trace the different evolutionary pathways a galactic heart can take, from a violent, brilliant youth to a serene and settled old age. The neighborhood a galaxy calls home profoundly shapes the destiny of its heart. Far from being solitary islands, galaxies exist in a vast cosmic web, from sparse, quiet fields to densely packed urban clusters. In these crowded galactic cities, the core's life story is often cut short. As a galaxy moves through a dense cluster, it plows through a superheated fog of gas known as the intracluster medium. This creates a powerful wind, a phenomenon called ram pressure stripping, that acts like a cosmic sandblaster. It violently tears the galaxy's own cool gas right out of its grip. This gas is the lifeblood of the core, the raw material for new stars and the sole source of fuel for the central black hole. With it stripped away, the core is starved. Its stellar nurseries fall silent, and the supermassive black hole, deprived of sustenance, slips into a deep and permanent hibernation. The core's transformation is forced into an early and abrupt retirement, leaving it a quiet, reddened relic. Yet in the isolated vastness of the cosmic field, a galaxy experiences a completely different existence. Here, it evolves at its own leisurely pace, largely free from disruptive gravitational encounters. It can hold onto its precious gas reservoirs for much longer, allowing for a more extended and self-directed evolution. Its core may continue its slow, internal transformation through secular processes, gently building its central star cluster and occasionally feeding its black hole in a measured, sustained rhythm. This stark contrast reveals a profound truth. The environment acts as an external clock, either hastening the core's journey to old age or granting it the gift of a prolonged, active life. It adds a critical layer of destiny to the core's story, reminding us that a galaxy's fate is not written solely from within, but is also imposed from the vast structures of the universe itself. Our own galaxy's quiet heart is living on borrowed time. The supermassive black hole we call Sagittarius, a star, currently slumbers, a gentle giant in our cosmic backyard. But this tranquility is only a temporary chapter in a much longer story. The future of the Milky Way's core is already written in the gravitational pull of our closest neighbor, the Andromeda Galaxy. In approximately 4 billion years, these two great spiral galaxies will begin their slow, inexorable dance toward a merger. This is not a rapid collision, but a drawn-out gravitational embrace that will fundamentally reshape both systems. During this cosmic construction project, immense tides of gravitational force will wrench stars from their orderly orbits, and most importantly, will funnel absolutely colossal amounts of gas and dust directly into the galactic center. This is the trigger. Our dormant black hole, Sagittarius, a star, will suddenly find itself at the center of a torrential downpour of fuel. As it gorges on this incoming material, its accretion disk will blaze to life, and the core of our galaxy will ignite as a quasar. For a time, this single point of light could outshine every star in the merged galaxy combined. Simultaneously, the same inflowing gas will compress, triggering a ferocious burst of new star formation right in the galactic heart. The core will become a brilliant, chaotic factory, producing millions of new stars in a final, spectacular firestorm of creation. This brilliant but destructive phase cannot last forever. The quasar's own incredible energy output will eventually heat and blow away the remaining gas, starving both itself and the new stellar nurseries. The brilliant flash will subside. What will be left is the calm, red glow of aging stars within a new, more massive elliptical galaxy. The dynamic, spiral structure of the Milky Way will be gone, replaced by a smooth, featureless core. Our galactic center's present quiet is not an ending, but merely a peaceful interlude in a billion-year saga of violent change and rebirth. Our ability to witness this billion-year story hinges entirely on a technological revolution in how we see the cosmos. For centuries, our view from the ground was blurred by Earth's own atmosphere, a shimmering veil that distorted the light from distant galactic hearts. The breakthrough came with adaptive optics, a system that uses a laser to create an artificial guide star, measures the atmospheric distortion in real time, and then commands a flexible mirror to change its shape hundreds of times per second to cancel out the blurring. It is like putting eyeglasses on a giant telescope, granting them crystal-clear vision to resolve the frantic dance of stars around our own Milky Way's central black hole. To escape the atmosphere entirely, we launched our eyes into space. The Hubble Space Telescope, and now the James Webb Space Telescope, act as ultimate time machines. By staring for days at a single patch of sky, they collect the faintest photons from galaxies billions of light years away. This allows us to look back in time and directly observe galactic cores in their youth, capturing them during their violent quasar eras and chaotic mergers, providing snapshots from across the entire narrative of cosmic evolution. But simply seeing these cores is not enough. We need to understand their inner dynamics. This is where spectroscopy becomes our most powerful tool. By splitting a galaxy's light into a rainbow of colors, astronomers can read fine lines in this spectrum that reveal the composition, temperature, and most importantly, the velocity of stars and gas. It is how we measure the incredible speeds of stars whipping around the galactic center, speeds that betray the immense mass of the hidden supermassive black hole pulling on them. No single color of light tells the whole story. The true portrait of a galactic core is painted across the entire electromagnetic spectrum. The searing X-rays detected by observatories like Chandra come from the million-degree gas just outside the black hole's event horizon, the final cry of matter being consumed. The faint radio waves picked up by vast antenna arrays trace the colossal jets of material being launched away at near light speed. Infrared light, where the James Webb Telescope excels, pierces through obscuring dust clouds to reveal hidden bursts of star formation. Each wavelength unveils a different chapter of the physical processes at work. The next leap in clarity is already on the horizon. The extremely large telescope, being built on a mountaintop in Chile, will combine a mirror nearly the size of a blue whale with these advanced technologies. It will have the resolution to see a car on the surface of the Moon, allowing us to watch individual stars orbit ever closer to the event horizons of distant galaxies. With such instruments, we will not just reconstruct the story of galactic cores from fossil evidence. We will witness their slow-motion transformation in real time, testing our models of black hole feedback and stellar dynamics against the ultimate laboratory of the universe itself. These ancient, dense stellar cities hold the deepest memories of the galaxy. Globular clusters are cosmic time capsules, each one a pristine ball of hundreds of thousands of stars, all born together in the galaxy's violent infancy. Their incredible longevity means they have witnessed the entire epic of galactic evolution, and their slow, inevitable drift toward the center makes them perfect archaeological tools for deciphering the core's past. The mechanism that draws them in is a subtle but relentless force known as dynamical friction. As a massive globular cluster orbits through the galaxy's halo, its immense gravity creates a slight wake in the sea of dark matter and background stars. This gravitational wake, in turn, exerts a drag on the cluster itself, sapping its orbital energy. Over billions of years, this persistent braking action causes the cluster's orbit to decay, spiraling it ever closer to the bustling heart of the galaxy. It is a cosmic inevitability for many of these ancient systems. Once a globular cluster ventures too close to the dense core, it meets its end. The powerful and chaotic gravitational tides, primarily from the central supermassive black hole and the dense nuclear star cluster, begin to pull the globular cluster apart. They strip away its stars one by one, dispersing them into the swirling stellar population of the inner galaxy. This process is a form of gentle cosmic cannibalism. The stars from the disrupted cluster do not vanish, they are assimilated. Some join the glittering throng of the nuclear star cluster, while others are flung into the general stellar halo of the core itself. This accretion event permanently alters the core's demographic makeup. Each captured star carries a unique chemical signature, a tag that reveals its origin. Stars born within the main galaxy's disk have a certain chemical composition, enriched by generations of supernova. But stars from an accreted globular cluster often have a very different, more primitive chemical fingerprint. They are like immigrants who retain the accent of their homeland. By taking a detailed census of the stars in the galactic core, astronomers can identify these distinct groups. When they find a population of stars with identical, ancient chemical patterns and similar ages, it is a clear signal that a globular cluster was torn apart and absorbed at some point in the distant past. This allows scientists to not only identify that a merger happened but to roughly date it, piecing together a timeline of the construction events that built the core we see today. The very properties of a galaxy's entire system of surviving globular clusters provide another layer of evidence. A galaxy that grew through many mergers will have a rich, complex system of globulars with a wide range of chemical properties and orbits. A galaxy that led a more isolated life will have a simpler, more homogeneous collection. By reading this stellar archive, we can reconstruct the biography of the galactic core, understanding the sequence of violent acquisitions and quiet growth that ultimately forged the powerful engine at the galaxy's very center. Gravity may rule the galactic core, but it is not the only invisible hand at work. Woven through the chaos of stars and superheated gas are immense magnetic fields, cosmic filaments of force that guide the very currents of matter and energy. These fields are born from the churning dynamo of the galaxy itself, amplified by the motion of ionized gas across billions of years. When gas becomes hot enough, its atoms split apart into charged particles, and this electrified plasma becomes a slave to the magnetic environment. The fields act like invisible rails, channeling the flow of this gas along specific paths, preventing it from drifting randomly. This subtle guidance is crucial for the core's most dramatic events. When a supermassive black hole feeds, the magnetic fields threading its accretion disk are not passive observers. They are twisted into a powerful, coiled spring by the disk's furious rotation. This process can launch and tightly collimate the breathtaking jets of plasma that scream away from the galactic center at nearly the speed of light. Without these magnetic fields to focus and accelerate the material, these jets would likely be little more than a diffuse, shapeless wind. In the core's younger, more chaotic days, magnetic fields served another vital purpose. As gas swirled toward the center, it possessed angular momentum, a kind of cosmic spin that prevented it from falling directly inward. Magnetic forces provided a solution, acting as a cosmic brake. They could effectively transfer that spin outward, allowing the gas to lose energy and spiral ever closer to the waiting black hole, steadily feeding the growing monster. Even in quieter times, these fossil magnetic fields, trapped and compressed over eons, add a persistent pressure to the core's interstellar medium. This magnetic pressure helps support the weight of the surrounding gas, influencing its ability to collapse and form new stars. It is a layer of magnetohydrodynamic complexity, a silent, persistent influence that works alongside gravity to write the final chapter of the galactic heart's transformation. These ultra-compact dwarfs defy our simple categories. They shine with the light of millions of suns, yet are squeezed into a space just a few hundred light-years across. They are cosmic anomalies, too large to be a simple star cluster, yet too small and dense to be a typical dwarf galaxy. So what are they? The most compelling theory is a story of cosmic loss and survival. Picture a small dwarf galaxy with its own tiny central bulge and a supermassive black hole, orbiting a much larger galaxy like our own. Over billions of years, the immense gravitational tides of the giant galaxy act like a cosmic grinder. They strip away the dwarf's outer layers of stars and gas, leaving behind only its dense, resilient core. This stripped nucleus, the lone surviving heart of a devoured galaxy, is what we observe as an ultra-compact dwarf. If this is true, then every UCD is a ghost, the remnant soul of a galaxy that no longer exists, and this transforms our understanding of a large galaxy's core. The bustling center of a galaxy like the Milky Way may not be a single monolithic structure. Instead, it could be a graveyard of galactic hearts, a silent city built from the digested cores of countless smaller systems that ventured too close. Each major merger we discussed earlier did not just add stars, it potentially added an entire prefabricated core. The dense nuclear star cluster we see today might be a mosaic, assembled from the central engines of many devoured dwarfs. This idea of hierarchical buildup paints the most vivid picture yet of a galaxy's core. It is not born in one event, but constructed piece by piece over cosmic time. The supermassive black hole at the center sits like a monarch atop a throne built from the conquered hearts of its former rivals. Studying ultra-compact dwarfs gives us a way to test this dramatic history. By measuring their masses and internal structures, Astronomers can work backwards, estimating the properties of the original dwarf galaxies they once belonged to. They are living fossils, holding clues to the violent, democratic process that builds the majestic centers of galaxies. That final, spectacular merger of two galaxies leaves behind a lasting gravitational partnership in the core. The two central black holes, now bound together, begin a tight orbital dance. This binary system becomes a powerful gravitational engine, and its primary effect is to violently clear out the very heart of the new galaxy. As the black holes whirl around one another, their combined gravity acts like a chaotic slingshot. When a star ventures too close to this dancing pair, it gets caught in a complex three-body interaction. The binary can transfer a tremendous amount of energy to the star, flinging it outward at such incredible speed that it escapes the galaxy's grip entirely, becoming a hypervelocity star lost to the intergalactic void. This process, known as three-body scattering, is a remarkably efficient form of stellar ejection. Over millions of years, this relentless gravitational purging carves out a distinct region of lower density at the very center of the galaxy. Astronomers call this effect core scouring. The result is a visible deficit of stars in the innermost region, a hollowed-out core that is a direct fossil record of a past binary black hole at work. This scouring permanently alters the core's structure, leaving it less densely packed than it would have been otherwise. The final act in this drama is the merger of the two black holes themselves. As they spiral ever closer, they lose energy by rippling the very fabric of space-time, emitting gravitational waves. Their eventual collision is one of the most violent events in the universe, but its visible impact on the surrounding stars is surprisingly minimal. The gravitational waves carry away the final energy, leaving behind a single, more massive black hole in a now quieted and cleansed central region. The presence of these binary systems is therefore a crucial, destructive phase in the life of a galactic core, a mechanism that literally sculpts the stellar landscape by flinging stars away into the darkness. The very atoms that make up the stars in a galactic core carry the memory of ancient cataclysms. This chemical enrichment is a slow, cumulative process that permanently alters the core's identity. In the earliest chapters of a galaxy's life, the most massive stars dominated the scene. These giants burned through their nuclear fuel in just a few million years, a fleeting moment in cosmic time. Their deaths were not quiet. They ended in colossal supernova explosions, events of such staggering power that they forged entirely new elements deep within their furnaces. In their final moments, these stars scattered their enriched innards across the core, seeding the primordial hydrogen and helium with freshly minted heavier elements like oxygen, neon, and magnesium. This stellar ash became the raw material for the next generation. When new stars condensed from this now polluted gas, they inherited a specific chemical signature. They were born with higher concentrations of these heavy elements, a direct inheritance from the short-lived giants that came before them. This process creates a clear chemical clock. A star rich in alpha elements like oxygen and magnesium tells you it was born from gas that was enriched by those rapid, core-collapse supernova, the kind that mark a period of intense, early star formation. As the core matures, another type of supernova begins to contribute. Smaller, longer-lived stars eventually form white dwarfs. In binary systems, these dwarfs can steal material from a companion until they cross a critical mass threshold, triggering a different kind of explosion known as a Type 1, a supernova. This event predominantly floods the core with iron. So, the ratio of iron to elements like oxygen becomes a powerful diagnostic tool. A core with a high iron content relative to its oxygen suggests a more extended period of star formation, where these Type 1, a supernova, had time to occur and contribute their unique elemental signature. By taking a detailed chemical census of the thousands of stars in a galactic core, Astronomers can read this layered history like the rings of a tree. A stellar population with a uniform, alpha-element-rich composition points to a single, rapid burst of star formation that was quickly quenched. A population with a wide range of iron abundances, however, tells a story of a more prolonged and complex history, with star formation continuing over billions of years, each new star layering in the chemical evidence of its own eventual demise. The core's composition is therefore a living archive, a chemical fossil record that allows us to reconstruct the tempo and intensity of its most violent and creative periods, long after the light from those events has faded into darkness. The early universe was a crucible of cosmic violence, where the deaths of the first stellar giants left scars on the very architecture of young galaxies. Among those first stars were true behemoths, monsters hundreds of times more massive than our Sun. Their lives were spectacularly brief, ending not in a typical supernova, but in a cataclysm known as a hypernova. This ultimate stellar collapse is the engine behind long-duration gamma-ray bursts, the single most powerful explosions we know of since the universe began. For a few fleeting seconds, a gamma-ray burst can outshine every other star in the observable universe combined. These events are not random. They are deeply intertwined with the most fertile stellar nurseries in the cores of primordial galaxies, where star formation was rampant and chaotic. A gamma-ray burst is the unmistakable signature of a galaxy core in its most feverish and explosive youth. The local effect of such a blast is almost beyond comprehension. From its source, the burst emits twin jets of concentrated radiation, slicing through the surrounding gas and dust. Any nascent planetary system lying in the path of these jets would be instantly sterilized, bathed in a flood of high-energy radiation that would shatter atmospheric chemistry and scald surfaces. On a galactic scale, the impact is even more profound. The sheer force of the explosion can act like a cosmic pressure washer, violently ejecting enormous quantities of the core's precious gas reservoir out into the galactic halo or even into intergalactic space. This sudden loss of raw material would have an immediate and chilling effect on the core's future. The very fuel for the next generation of stars is ripped away. While these events were incredibly rare, their occurrence during the formative stages of a galaxy could not be ignored. A single gamma-ray burst at a critical moment might have prematurely quenched star formation in its immediate vicinity, effectively stunting the growth of the central star cluster. It could have robbed the infant supermassive black hole of its future meals, altering its growth trajectory for billions of years to come. The ghost of that ancient, unimaginable flash might therefore be frozen into the core we see today, a faint but permanent signature of a brief, brilliant, and catastrophic fire in the galactic dawn. These digital universes are built from mathematical laws, each one a cosmos in a supercomputer. To model the billion-year story of a galactic core, these simulations must account for an intricate cosmic dance. They calculate the relentless pull of gravity on both dark matter and visible stars. They simulate the complex flow and pressure of interstellar gas, a discipline known as hydrodynamics. They program in the rules for star formation, where dense pockets of gas collapse to ignite new suns. And most critically, they include the powerful feedback loops from supernova explosions and the intense radiation from active supermassive black holes. This last ingredient, the energy output from these events, is the crucial regulator that prevents simulations from creating galaxies that are too large or too bright compared to what we actually see in the night sky. With these rules in place, astronomers can press play on the universe. They seed their virtual space with conditions mimicking the early cosmos, then watch as gravity works its slow magic. From a nearly uniform primordial soup, filaments of dark matter emerge, and at their intersections, galaxies begin to condense. We can watch in accelerated time as a tiny, chaotic core in a young galaxy steadily transforms. We witness the violent ballet of galactic mergers, which funnel gas inward and trigger brilliant quasar phases. We can also observe the slower, more gentle process of secular evolution, where a galaxy's own spiral structure patiently channels material toward the center over eons. The true power of these models lies in comparison. By generating thousands of virtual galaxies, each with slightly different initial conditions or physical recipes, and then comparing their final cores to real galaxies observed by Hubble and Webb, we can test our theories. Does a simulation that includes strong black hole feedback produce the red, dead ellipticals we see? Does a model that emphasizes minor mergers create the correct distribution of nuclear star clusters? These virtual time machines allow us to isolate the impact of a single process, like a controlled experiment on a cosmic scale. They reveal, for instance, that without the self-regulating brake of black hole feedback, galaxies would grow to unrealistic sizes. They show how the Core-Cusp problem in dark matter might be solved by factoring in these cumulative energy outbursts. A simulation is more than just a movie. It is a dynamic test of our deepest understanding of physics, providing a living, evolving picture of a transformation that is simply too slow for any one astronomer to ever witness. One of the most compelling puzzles in galactic archaeology is the existence of vast, hollowed-out centers within some of the universe's most massive elliptical galaxies. These are not dense, brilliant hearts, but rather expansive regions of surprisingly low stellar density, as if the very core of the galaxy has been scooped out. The leading theory to explain these cosmic voids is a process called core scouring. This dramatic remodeling is thought to occur when two galaxies merge, forcing their central supermassive black holes into a tight binary orbit. As these two gravitational monsters dance around each other, their combined pull acts like a chaotic slingshot. Stars that wander too close are caught in a violent three-body interaction, receiving a tremendous gravitational kick that flings them clear out of the core region entirely, never to return. Over millions of years, this relentless stellar ejection permanently lowers the density of the galactic center, leaving behind the fossilized signature of a past merger. Yet the precise mechanics of this process remain shrouded in mystery. How efficient is this stellar purging really? Does it require the black holes to have a very specific orbital configuration to be so effective? Could other powerful forces, like the immense outflows from a single, feeding black hole, produce a similar hollowed-out appearance without a binary ever forming? Answering these questions is not just about solving a single puzzle. It is about reading the final chapter of a galaxy's most violent history, understanding the precise tools that gravity uses to sculpt the universe's densest stellar metropolises long after the lights of the merger have faded. The gradual transformation of a galaxy's core is an epic saga written in starlight and gravity. It is a story of chaos giving way to order, of brilliant, violent outbursts fading into a quiet and dignified maturity. We have traced this journey from the first collapse of primordial gas to the slow, internal grinding of secular evolution, from the blazing dawn of quasars to the serene glow of ancient stellar cities. Through it all, one truth stands clear. The fate of an entire galaxy, with its hundreds of billions of stars, is dictated by the tiny, powerful engine at its very heart. This cosmic narrative reminds us that the universe is in a constant, if imperceptibly slow, state of flux. Nothing is truly static. The centers of galaxies are not immutable monuments, but dynamic engines, their lives a series of construction, destruction, and rebirth playing out across billions of years. Their evolution is the central thread in the grand cosmic story, a story that continues to unfold around us. The next time you look up at the night sky, let your gaze settle on the faint, hazy band of the Milky Way. Know that within its quiet center, a story of immense power and patience is still being written, a testament to the deep time and profound changes happening in the heart of every single galaxy. This incredible journey through cosmic time reveals a universe of constant, majestic change. If this exploration has ignited your own curiosity, you can help this channel continue its mission by liking this video and subscribing for more deep dives into the universe's greatest mysteries. We want to hear what resonates with you most in this grand story. What aspect of galactic evolution captures your imagination? Is it the terrifying power of supermassive black holes to shape entire galaxies, or the slow, patient ballet of stellar dynamics that constantly remodels the core? Share your thoughts and questions in the comments below. Your perspective enriches this conversation for everyone. For those eager to venture further, we have included links in the video description to some of the groundbreaking research papers and the breathtaking observatory images that allow us to piece together these galactic biographies. They are your portal to the front lines of discovery. The story of the cosmos is written above us every night, a silent, ongoing epic of transformation. Keep looking up and never stop wondering.